All right, so let's go ahead and take a look at a test on a population mean. So we're down here in our section. We're going to start looking at the testing and see how it plays out. And again, we'll go very quickly through our 5 steps that we've talked about a few times. And let's start with the first one. Here's our sample hypothesis test, and I'll use one of the examples that we saw before. We want to test that some new machine is going to reduce our cycle time to below 12 minutes. So our first step is to state the null and alternate hypothesis statements correctly. And here we'll have our alternate statement that says our population mean. So we'll be talking about our average cycle time. This is not a proportion of any sort. So we would look at our average time in the past being 12 minutes, and we'd take some sampling. We'd be looking at the average time to see whether it supports the claim that on average our cycle times will be below 12 minutes. So the alternate statement would be that mu, population mean, is less than 12 minutes. The null statement would be the complement of this, that mu is greater than or equal to 12 minutes. So we've got our null and alternative statements. We need to specify a level of significance for the test, and we'll just take a value of 0.05, a 5% significance level. What's the test statistic we're going to use? Well, we know that we're dealing with a sampling distribution of sample means. So we're going to model that with the t-distribution. So we're going to have to figure out what the t-value is for our given sample. So we get the sample mean from our test sample, and our standard error is going to be s over the square root of n. You'll remember this from our discussion on sampling distributions. So we're going to find out how far away our t-value is, how far away, our sample mean is, x bar, from 12 in standard errors. So we're going to take our x bar minus 12 divided by the standard error, and that's going to give us our t-value. So that'll be our we're going to be finding a t-test statistic, and that's what we're going to use to determine our p-value for the test. Let me give you a visual of what this looks like. All right, here I'm showing you a t-distribution, and this is going to be for our sampling. Is going to represent our sampling distribution that's centered around our null value of 12. So the mean of this distribution, the peak, is going to be right at 12. And let's suppose we have a sample mean. So I've gone out now with this new piece of equipment or new process, and I've measured the cycle time for 15 runs of this process. So my sample size is 15. And I found that I have a sample mean of 11 minutes and a sample standard deviation of 3 minutes. So I find my sample standard deviation, I find my sample mean. So what's the t-value? What's going to be x bar, which is 11, sample mean, minus the null value, 12, divided by s over the square root of my sample size, which is 15. And it turns out that gives me a value of a minus 1.291. And that's going to be my t-value for this test. And that's going to give me a roughly here on the curve, a minus 1.3 for my t-value, corresponding to an x bar, a sample mean of 11 on this sampling distribution that's centered at 12. So I have my t-value, and when I go to the next step, which is to conduct the test and make my decision, what I'm trying to find is the p-value. What's the probability under this sampling distribution that has a mean at 12 and a standard error of 3 divided by the square root of n? What's the probability of being at least as far away as my sample in question on the side that would support my claims? I'm only interested in the probability of the tail on this side. It's a one-tailed test, because if you go back to the alternate hypothesis statement, it was mu is less than 12 minutes. So it's a one-tailed test. I'm just interested in this red shaded area here. And to find this, I would use in Excel my t-dist formula. I'd have to put in the absolute value of t here, because the t-dist formula likes a positive t-value. I would put in my number of degrees of freedom, which is going to be 15, my sample size minus 1, so 14 degrees of freedom, and then I would put in a 1, because I only want one tail. And let's see what that looks like in Excel. Should be fairly straightforward to do. If my n is 15, my t value is going to be, well, let's do the whole thing. Let's say what my sample mean, that's going to be my x bar, okay, is 11. We'll go through all of the calculation. My s, my sample standard deviation, I said was 3. So I can find, and let's put in my null value of my mean is going to be 12. Okay, so let's calculate the t value. That t value is going to be equal to, I'll put in parentheses here, my x bar minus my null value divided by my standard error, which is going to be, I'll put this in parentheses again, even though I may not need the parentheses here, s divided by the square root of n. One more parenthesis. Okay, so the numerator here is x bar minus mu divided by the standard error, which is s over the square root of n. And I get a minus 1.9, the same thing that I had gotten from the little Java applet here, a minus 1.291. 29099, so minus 291. Great. So what's now going to be the p-value? That p-value is going to be the probability of being further out in the tail. And I'm going to have to use my t-dist formula to find that out. It wants a positive value of t. So I'm going to just take my absolute value of my t just to make sure I'm getting the positive value. And we're going to utilize the symmetry here. So because I have to put in a positive value, I'm going to just take the mirror image of this centered around the mean. So imagine just flipping this over, and the area that's on the right hand side of a positive 1.291 is going to be exactly equal to this red shaded area here. So that's what I'm calculating. So I'm putting in this absolute value of my t value. So it'll be a positive number going in for t. My number of degrees of freedom is going to be n minus 1. And then do I want a one-tailed distribution, a one-tailed probability, or two-tailed? In this case, it's a one-tailed test. So I'm going to put in a 1. I want a one-tail of this distribution. I hit enter. And I get a p-value of 0.1088. Same thing that I got from on this applet here. So the shaded area is what I'm trying to calculate. That's my p-value. It's a probability of a random sample from a population that is at 12 minutes being at least as far away as the sample in question. So in my next step of the process, I'm going to compare this p-value to the significance of my test. And my significance was 5%. So if my p-value, if this probability of this sample or any or a sample more extreme than it being from this null distribution is anything greater than 5%, I don't have strong enough evidence to reject my null hypothesis. And in this case, my p-value is just over 10%. So my conclusion would be that no, my p-value is not low compared to my significance. It's higher than my significance. So therefore, I'm not going to reject the null hypothesis in this particular test. So I would have to return to the and say, no, I don't have enough evidence to reject my null hypothesis. This would show me the sample evidence it's not strong enough to support my claim, because I'm not rejecting the null hypothesis. So hopefully that's clear. Because my p-value was not lower than my significance, the evidence is not strong enough for me to reject the null hypothesis. So I have to retain the null hypothesis. I'd have to say, no, this shows me that my population mean is not less than 12. Therefore, it's either at 12 or it could even be higher than 12, but certainly there's not strong enough evidence to support the claim that it's less than 12. So this is how we would carry out hypothesis testing. This is what we're doing. We're going to, again, consider a sampling distribution based around the null value, take our test sample and see where it would fall on that distribution, and then calculate the probability of a random sample from the null distribution being at least as extreme. And if that is sufficiently low, below 5% or below whatever significance we have, we would reject our null hypothesis. And in the example I just showed you, the evidence was not strong enough to support the claim. So we can also conduct tests on a population proportion. And again, the idea is very similar, same approach. Really, the only difference is that the sampling distribution is going to be modeled by the z distribution and not the t distribution. And we have a different formula for the standard error. That formula is going to be the square root of, as we'll see here, the denominator in this expression, the square root of our null proportion times 1 minus that null proportion divided by n, all in the square root. And this is exactly what we talked about for when we talked about the sampling distribution that we used to estimate a population proportion. The only very important difference here is that when we were doing confidence intervals and estimating a population proportion, we obviously didn't have a value of population proportion to put into this expression for the standard error that you see in the denominator here. So we had to use p hat. We had to use our point estimate, our sample proportion. But we only did that as an estimate. In this case, because when we do hypothesis testing, we're basing it around the null value, we always have an accurate population value to put in as p sub 0. So always remember when you're doing hypothesis testing, the value that goes into this expression for the standard error that you see in the denominator is going to be our actual null proportion, not our sample proportion. Using the sample proportion in the denominator here will only lead to inaccuracy and could lead you to the wrong result. But once we have this, we follow exactly the same approach as we did for our hypothesis testing on a mean. We're going to find our sample proportion, and we consider a sampling distribution of all the possible sample proportions we could get, and we know that it's going to be modeled by the z distribution centered at the null value. So our z value is going to be p hat minus that null value divided by the standard error. How many standard errors is our sample proportion away from our null proportion? And then we would use the norms dist formula to find the p-value from this, the probability of being at least as far away as the sample in question. So in this case, we take our z-value, and again, just to make it generic to whether or not the z-value is positive or negative, I use an absolute value here, and I treat it as though it's a positive z-value. So if I want the probability of being at least as far away as some positive z-value, it's going to be 1 minus norms dist of that positive z value. So by using absolute, taking the absolute value of z, I'm always treating it as a positive z value. And if it's a two-tailed test, I always have to remember to multiply that probability by 2. So my p-value in a two-tailed test is going to be the probability out in both tails that's at least as far away as my sample in question. And I'll actually illustrate that just going back to this test. If this, I'm showing you the example we were just talking about for our test on a mean, but if that were a two-tailed test and my sample came out here with a t-value of a minus 1.291, to find that probability, I would have to actually take this shaded area and multiply it by 2. Because for a two-tailed test, I have to remember that a sample that's out on my right-hand side more than 1.29 standard errors also is at least as far away as my sample in question. So I'd actually have to consider the probability out in both tails of the distribution if I was doing a two-tailed test, and just have to remember to multiply whatever I calculate for my shaded area from the t-dist formula. Well, when I put 2 in my t-dist formula, it'll automatically multiply it by 2. If I'm using the norms dist formula, I have to remember to multiply it by 2. All right, so that steps us through actually conducting this test on a few different scenarios, and we'll look shortly at some examples, and we'll see how those work.